Yeah, thank you very much, Roger, for your kind introduction. And so I hope it should go from the slides. So welcome everybody. And so does it change? Yeah, it changed. So first of all, I'd like to say a few words to Fraunhofer Society because maybe some of you don't know our institution. So we are an institution for applied research of direct benefit to private and public enterprises. And in Germany, so we have about 32,000 employees all over, 76 institutes and research institutions. We have a total volume business of 3.4 billion euros. And the major part comes from direct contracts with industry and from public funded research projects. So with this, oh yeah, it's a bit slow, but it works. So here a slide what we are doing. So first of all, on the left-hand side, we do synthesis and upscaling of new flame retardants from milligram to kilogram scale. You can see our kilogram lab here in the left-hand side. We do formulation of thermoplastics, thermosets, and elastomers according to specific requirements. And we are using both own flame retardants and ones that are in piloting or are commercially available. Last not least, we can do characterization and testing. So we do have UL94 cone calorimetry and LOI, and we do have testing equipment for glow via ignition test, comparative tracking index, and high voltage tracking resistance as well. But now coming to the first part, as you know, flame retardants are often needed in several applications, and they are derived from fossil resources and often halogenated compounds. And I will show in the first part bio-based alternatives for P-containing flame retardants, and Michael will cover the alternatives for halogen-free flame retardants in his part. First of all, I'd like to point out the motivation and cover the demands on not only bio-based, but also bio-based flame retardants. So they have to fulfill legal requirements. They need to be toxicologically safe. They need to be stable at processing temperature and processing conditions. You should have a reliable supply chain, and the chemistry you are using should be as much as possible green. And you should have a high bio-based carbon content. So if you look at the bio-based version, and finally, you should have compatibility with the polymer matrices you are targeting for, and it should be cost efficient. There are two principal ways of coming to bio-based flame retardants. So the first upper one goes from renewable raw materials, bio-based renewable raw materials to platform chemicals first. And these platform chemicals are then built up to new flame retardants. This is one approach. And the second approach is to modify the macromolecular raw materials from nature by introducing, for example, phosphorus containing groups. I go first on the way from macromolecules. Here, several years ago, we introduced the modification of cellulose by a mixture of acrylic and butyric acid anhydride. So to come up with this, I hope you can see my arrow. So by come up with this molecule and by using phosphorylated derivatives of this erythrit, which is a sugar alcohol, you end up in a molecule like this, where you have phosphorus modification realized. And you can start here from inexpensive renewables. So the synthesis way is without chlorine chemistry, which is good. And as it is an addition reaction, it is also atom efficient. Here there are some results from the bio-based flame retardant I showed you with 10% of of it in the formulation, and here you don't reach any classification by UL94. And the same is true if you go for this polyterbutylphenol disulfide, which is often used, so you can't reach a classification as well. And so if you compare it, for example, with antimony trioxide and bromodiphenyl ethane, so you can see that you reach a V2 classification, and the same is true if you use our new flame retardant in conjunction with this disulfide. You also get a V2 classification. We also tested this flame retardant in a partially bio-based polyamide. It's a Ultramid Flex F29 from BASF. And you can see, and it is compared with the DPAL as a very well-known flame retardant for polyamides. So the DPAL gets a V0 classification, and we are close to a V0 classification. We have one time a tripping, burning tripping, so that we then have a V2 classification. So as I said, compatibility is important, and if we start from organic cotton and introduce this two substitution patterns, one time the butyric acid for compatibility was the reason, and here this acrylic acid group in the macromonomer. And so we react this with the PAR I showed you. We end up in a macrophase separation when we put it in polyolefin, as you can see here on this slide macroscope. So with 10% of the flame retardant, so which is not wanted. In order to depress this, so we came up with a different solution. So we started from total chlorine-free celluloses, which comes from wood. And so we changed the reaction conditions a little, that we ended up in a diacrylate substitution pattern here in this unit. And if you do so, you can see here the micrograph on the right-hand side. If you compare this with the previously shown one on the left-hand side, so you can see that the macrophase separation is suppressed as much as possible by this approach. And if you compare the UL94 performance, so with the first and the second one, so you essentially end up in the same classification. So there is no difference in the flame retardant performance, and it is comparable with a Aflamid PCO 900 based formulation. So it gives you a V2 classification. So to end up, or to summarize this section, I hopefully could show you that we could design novel cellulose-based flame retardants, that we use the principle of green chemistry, because all the carbon we introduced was based on renewable one. And we started from wood pulp. We could design the structure by controlling the molecular weight, the substitution pattern, and the degree of substitution. And this is variable in a wide range, so we will still have some questions to answer. And our current status is a V2 classification in polyolefins and polyamides. In the last one, with a potential to reach V0. Further, we want to do further synergistic mixtures, so to even reach a better classification in UL94. And we will, in a follow-up project, we will look in application-related testing of the flame retardant and of other properties like the long-term behavior. Coming to the second approach, when we start from platform chemicals, our concept here was to introduce both condensed phase component and gas phase component within one polymeric backbone. And by by tailoring the environment of the phosphorus, we can say, okay, or we can tailor the gas phase or the condensed phase activity. Here I show you the one-pot synthesis, how this was optimized. So we came from this here hydroxy ethyl acrylate. So, and we reacted it to, in this case, with dichloro or trichloro components. So to have here chloro molecule atoms introduced, and we have this remaining acrylic acid groups. So in the second stage of the reaction, we reacted these acrylic acid groups with DOPO, which is known for its gas phase activity, and we came up to this molecule which has some acrylic acids left that could be polymerized, and we ended up in here 4 different molecules differentiating in the environment of the phosphorus. And here there is one commercial flame retardant, this itaconic based DOPO derivative, which we used for comparison as well. You can see here on the left-hand side that the thermal stability of all the new flame retardants is in the range of 280 to 290 degrees C. And here you can see that I focus on the comparison with the itaconic based derivative, where we used 15% up to 15%, and we only reached V0 in PLA compounds. And when we used our flame retardant with 10%, we could end up in a V0 classification. We also did synergistic formulations with APP, ammonium polyphosphate. And you can see here that you need more than 20% to reach a V2 classification. And when we go to mixtures with a low amount of APP and one of or two of our flame retardants, we could reach up to a V0 classification in case of DFR3. Yes, and our partners, Fraunhofer Umsicht, did the life cycle analysis regarding the CO2 equivalence here. And here on the left-hand side, you can see the CO2 carbon footprint for the flame retardants itself. You can see they are higher than the comparison, so which is the APP reference. But if you go to the formulations where you use the synergism, so you end up in a 20% better CO2 carbon footprint for the formulations, which is quite nice. Finally, we also tested some derivatives of this flame retardants in polyamide 6. It was in this case the aluminium salts that we used. And we found out that when using 5% of melamine cyanurate, which is typical for as flame retardant in polyamide 6, we end up in a V2 classification. And if we go to one of those flame retardants, we could reach a good synergism to melamine cyanurate with that just 0.5%, and we could end up in a V0 classification. But this effect was only visible for this compound here. I'd like to summarize also this part of my talk. So we could develop a one-pot synthesis for new flame retardants based on bio-based platform chemicals. And these new flame retardants contain phosphorus in different molecular environment. And we could identify visible synergistic effects with APP in PLA so far and MC in PA6 with UL94 V0 classification at 1.6 millimeters. And the outlook here, of course, is so to further test application related properties and other properties. And yeah, with this, I'd like to just point out the new industrial joint project that we are offering in our house, which has to do with the compounding of PFAS-free flame retardants, and we are searching for interested industrial partners. If you need more information, you can go to our website, or you can just email me and we can arrange a call, because this would now is now too much to point out here. So if you are interested, please let me know. I'm happy to introduce some more on this. With this, I'm done, and I hand over to Michael for the second part. Thank you very much for your attention.
Thank you, Frank. I think I have the power now to shift the slides. So I want to welcome you to my talk on the second part of this presentation, and it will cover the topic of the, let's say, newly structured flame retardants, the oxyamides. And first of all, good morning to the ones in North America, and good evening to the ones in Europe. And I will start. So the oxyamides are or were developed, let's say, about 10 years ago in the Fraunhofer LBF, and we did several. No, is it working? Yes. So why did we develop the oxyamides in the first place? If you go and look in the performance of a flame retardant plastic, so it's mainly depending on the loading of your flame retardant you put inside. So the more flame retardant you put inside, the more it influences or even determine the polymer performance. So our target was to decrease the loading of the flame retardant in the polymer, and to increase the performance and have a safe flame retardancy. This is probably the main reason there. For example, here you see the known flame retardants, and an example of polypropylene, which you all know. If you add 80% of a mineralistic flame retardant, you have basically the properties of those mineralistic fillers, and you lose all the or most of the polymeric performances. So, but if you lower the concentrations on your flame retardants, you get better performances. So our goal was to develop the gas phase active flame retardants, and we went back to the alkoxyamides, which were introduced by CIBA 25 years ago, a bit more than that. And it was a new class of flame retardants then. And you see here the example of from the flame stub NOR 116 from BASF. And this was probably the well-known one of this class of gas phase active flame retardants. And they have some advantages, also some disadvantages. The advantages are they are really efficient in low concentrations, especially in films and fibers. And they also have synergistic activities with other flame retardants. So there are, I will come later to that in detail, but there are several flame retardants that work quite well as synergists for those oxyamides. And the contribution to light stabilization, long-term stability is also given because they could work in this field. And the disadvantages, of course, they have sometimes, so it's not a general thing, but some of them have poor thermal stability at compounding. So if you have probably one of those flame retardants that decomposes at 200 degrees, you cannot use it in a polyamide, for example. But you should use it at the perfect polymer to compound it, therefore. In thick sections, they do most of the time not work as a single flame retardant, but they could work therefore as a synergist there. And UL94 V0 is sometimes difficult to achieve, and I will get later a bit more into that, because they work as a they increase dripping, and therefore, as you probably know, if it starts burning at some point and the burning drips away, you don't get V0, but it could easily get V2 at some point. So, as I mentioned that before, that they could work as a light and thermal stabilizer, and here's the reason why. So if you, depending on where the energy comes from, so if you have a flaming, or if you have a light induced or thermal induced energy that comes into the system, you have a breaking of the bonds here, and even the bonds between the nitrogen and oxygen, or the one between the alkyl rest or the oxygen, could split there, and you get different kind of radicals built there. And depending on those radicals, they behave as a flame retardant or as a light and thermal stabilizer. And during incineration, the NOR initiates a fast polymer degradation, because you have really active radicals built there, and those started the dripping in the material. So our new class of the oxyamides we introduced here, they are quite manifold, let's say that way. So there are aliphatic aromatic structures you see on the left top side. There are the polymeric structures you see on the left bottom side, salts, and also we added different heterogeneous atoms like phosphorus, sulfur, and all of them are working at some point at different applications and also different polymers, better or worse, but they work on the one hand as a flame retardant, but on the other hand also, as I mentioned before, some of them also could increase the flowing of polymers, because they decompose at some point and increase the flow of a polymer. Also, we can go beyond those structures. For example, we can do ethers, and we have the polymer analogous reactions. You can see on the top right side, the top left side, the reactive groups, and also the ether structures, which work really well in PBT, for example, and polyamide. We cover those by patents. You see them on the bottom side. For any questions there, just reach out to me afterwards. The synthesis on those different structures are quite easily to obtain. You see one example here on top. It's the Einhorn variation of the Schotten-Baumann reaction. So it's straightforward chemistry. As Frank said before, so we do chemistry in a house that needs to be easily adapted to a bigger upscaling, let's say that way. So everything we're doing here is on a purpose to make an industrial-sized upscaling in the end. There's also the Williamson ether synthesis. You probably know that, it's really famous, which to produce the ethers. At some point, it's not working, depending on the structure. So sometimes it's better to use the amide ether synthesis for the methylamino-phenol, or for DMAP for short. And both syntheses work quite good there. And as I mentioned before, there are a lot of synergists working really well with the oxyamides, and we tested a lot of them, let's say it that way. There are data on all of those who you've seen here. The thing is, I cannot touch all of the data in this presentation. I will show you some examples. For any further interest in anything, we could have a talk later on. Just reach out to me. And as you see, there are a lot of phosphorus and other nitrogen synergists, but also mineralistic synergists, but also brominated flame retardants. So in addition to the degradation temperature, a flame retardancy mechanism has to be considered here. And you see it on the right side. Normally, if you have a burning and a dripping, you see that burning drips going down, and the oxyamides, they start the dripping, and you see you have more like a flow which goes through, and you have a fast dripping. So therefore, the material puts itself out of the flame, and the gas phase is active. It's reacts with the flame itself, with the oxygen in the flame, so you don't have a reaction there. So we have a fast tripping of the polymer, the gas phase reaction hindering the flame to let the polymer burning, and the radical reactions with a synergist, if you have, for example, like here a bulky material that improves this working. So we have synergistic gas phase activity preferred here, and those are normally the aliphatic phosphonates or phosphocines. The first example is for the polypropylene systems. So if you look here for polypropylene, we use the oxymide seen on the right side. We call it the FR300, and the phosphonate on the bottom, it's the aflamid 900 from Tor. And you see we have different formulation that all leads to the solid V0 classification and a really low burning time. So at 1.6 millimeter, we get here loadings from 8 to 10% for V0, which is really good. And also the mechanical properties were almost obtained, and you had a really good flexibility from polypropylene here. In general, when we look through all the data, you know this number, so 60 to 70% of magnesium hydroxide, brominated flame retardants with antimony trioxide around 30%, or ammonium polyphosphate around 20 to 30%. So we get, depending on the polypropylene, of course, a V0 at 8 to 15%. So the oxymid radical generator system shows really low flame retardant performance at a really low loadings here. And going on with the same system for the oxymide and the synergist, the second example, and also at 1.6 millimeter specimens, you see for different types here, in this case for polyethylene, we have every time 70% total concentration, so 2% oxymide and 15% of the phosphonate. We get a V0 with very low or no burning time. And also here, you see the known concentrations for mineralistic, like aluminum hydroxide, or the brominated flame retardant with ATO, or the ammonium polyphosphate. And the comparison loading for the oxymide system is quite or really low here. We even got at some point one polyethylene which got a V0 at 12%, but as I showed you before, so 17% is most of the times quite sure to reach the V0. So also here, the very low loadings to get a really good flame retardant performance. What we did a few years back was a study with TPUs, and we tested them in 1.6 millimeter tests. So we used different known flame retardants that work really well. The TPU was an Elastolan 1185A. So the blank did burn and did not classify under UL 94. But as you see here, there are some classic formulations and some classic flame retardants that work also really well to get a V0. And as I mentioned before, especially in TPU, you get a really good flowing of the material, but sometimes some of the burning parts strip down, so you didn't get the V0 classification, but it was on the edge, let's say it that way. So if you see the number 7 with the oxymide 2% and 10% of the dipal, which worked really good in a synergistic mixture here, you get a 12% loading and a secure V2 and almost a V0. So it's on the edge, let's say that way. Probably one could increase one or bit to get a solely V0. But we got a V0 at a complete loading of 17% with 2% of an oxymide salt. And as I showed you before, there are some possibilities to get the salts, and they are also working quite good. For further things, which is some things that came to me, let's say, the last month or half a year, the replacement of antimony oxide in some formulations. So this is something we looked into, and it is possible to exchange antimony trioxide to an oxymide, which you see on the formulations 2 and 3. So we got the V2 classification UL94 at 1.6 millimeters for the 2% oximide, or alternatively, if you use 7.5% of the ATO, to get it to probably almost the same result. If you go completely halogen free, and you see those both two on the bottom, you could of course go down to 10%, and if you make the right flame retardants and synergistic mixtures, you can also reach a V0 here, which is also possible. In polypropylene was this example here. And finally, some of the things we've done not so long ago, we looked into polylactic acid polymers, so it's PLA films, in this case at 118 microns. And we looked at the film test, the DIN 4102 B2 test, and the blank material itself, it fails the test, and it starts burning. But if we use just 1.5% of our oximide, it passes really well. You see it on the right side here. We tested several different oximides in this sessions, and they all pass, some better, some worse. Like you see some opaquening of the films for some of them, like here for this one. You have some that do not opaque, but they are a bit worse in the flame retardancy, so something like that. And also, if you ask what's the other things in the market that could can be compared, so the NOR 116 also passes here. So, but the here the oximide on the right side, the FR 300, worked the best in this test. And so to summarize everything, so the performance in olefins, especially at a glance, was we got polypropylene loadings that could go at some cases as low as 5%, and polyethylene loadings that could get as low as 10%. It's in extreme cases, depending, as I said before, in the depending on the polymer. And we got polyolefins, homo and copolymers with different MFR values that were tested over the time, and different sample thicknesses that were tested from very thin 0.2 millimeters up to 4 millimeters to reach V0. And also PLA was tested as V0 at 1.5% without any synergistic flame retardants there. And in addition, the oximides could be used also in TPU at loadings from 12 to 15% to reach a classical V2, but also in synergistic mixtures like the one I showed before with 17%, which reached a V0 there. And also could be used as a substitute for antimony trioxide at slightly lower contents compared to the antimony trioxide. And just to give you a take-home message, not just the oximides, so in general, radical generators are important class as really efficient flame retardants and flame retardant synergists. So oximides them show outstanding performance in several polymers, and I didn't show you the polyamide and polybutylene terephthalate results because it would be too much for this presentation. But this is something you could reach out also to me if you want to discuss that. We got also quite low loadings there, and they work quite well, and also as synergistic mixtures. And the degradation temperature of the oximides, they are adjustable, and between 100 and we have also some that go up to 380 degrees, which you should think about then for the polymer and the application in the end. So different plastics and their applications are accessible with different structures, therefore. And the combination with phosphorus synergists improves the flame retardancy as to reach, let's say, a V0 for almost all of the polymers we've tested here. And in general, very low loadings in total, and especially for the polyolefins. And oximides are efficient antimony trioxide alternatives, also for halogenated flame retardants. And you could, of course, exchange completely your formulation to make a halogen-free flame retardant solution here. And the upscaling in a ton scale has already been carried out by an industrial partner, and this is possible and feasible. And at the moment, we are open for industrial partnership. If someone is interested in working with these oximides or want to make a market launch together with us, feel free to reach out to me, and we could bring this ship into the market or in the oceans, let's say that way. And as my colleague Frank before, I would just make a small broadcast here. As Roger said before, I worked a lot on the flame retardancy of recyclates, and we will start this year in September this industrial joint project where we gather together a group of companies that all work and pay on this field of this upcycling of recyclate materials, and also look into the recyclability of these materials. And of course, this time we did those studies together with Pinfa companies from Europe over the years. And this time we also go with real upcycled materials from post-consumer recyclates, flame retarded post-consumer recyclates, and we will look how is it possible to improve those materials to the high standards we need in end products, and how do they last if you make like closed loop environments we will probably have in the future as future quotas for materials come up. And I want to say thank you very much, and I appreciate that you listened to my talk, and feel free to reach out to me afterwards or answer here. And as I see, there are a lot of questions already asked, and thank you very much.
Thank you very much.